Good evening, everyone. I welcome you to the last seminar talk of the Digital to Classicist seminar series in this term. As usual, I hand around the attendance sheets to sign in. And then I have the pleasure to present our today's speaker, Mrs. Aline Deicke. She's from the Academy of Science in Mainz, where she's working till 2009, I think, in a project which is called Digital Academie. So that's an affiliation to the overall topic here as well. Her personal background is that she studied prehistorical archaeology, classical archaeology, and anthropology in Mainz, in Pécs, and Budapest. And you will see that the background from her talks today is an archaeological research question. She worked for a couple of years at the Römisch-Germanisches Zentralmuseum in Mainz as well, before and then changed in 2009 to the Digital Academie, where she's responsible for a couple of projects and infrastructures which the Academy is doing. The talk today is part of her dissertation project, and as you see, covers from E19 to match and merge, and what that means she's going to present. Thanks for coming, and it's yours.
Yes, dear Felix, thank you for the kind introduction, and thank you for the opportunity to speak here today at the last session of the Digital Classicist. I heard there will be wine afterwards, so I will try not to keep you too long. As Felix already said, I'm from the Digital Academy of the Academy of Sciences and Literature in Mainz. The slides for this presentation, if there's an aspect of the presentation you want to follow up afterwards, the slides are on GitHub pages under this address here. So, and I linked all the necessary or the important resources in case anyone is interested in following up. The title of my presentation, From E19 to Match and Merge, I will talk about mapping the CIDOC CRM to graph databases as an environment for archaeological network research. I've divided my presentation in 4 parts. First, I will talk a little bit about my PhD project, Formation of Elite Identity in the Late Urnfield Culture, which was the context in which I have developed this kind of workflow. Then I will come to the main subject, CIDOC CRM-based graph databases. First, I will say a little bit about graph databases, a little bit about the CRM, and then about the data model, which I use in my project. And then I will give a little walkthrough through the whole workflow, how you would go on with doing archaeological network analysis in conjecture with graph databases. And lastly, I will give a short outlook and conclusion. Okay, so the title of my PhD project is Formation of Elite Identity in the Late Urnfield Culture as reflected by funeral status representation. As the title already gives away, it deals with elite burials of the Late Urnfield Culture and the identities that are transported through objects that are contained in these graves. I'm sure not everyone is familiar with the term Urnfield culture. The Urnfield culture is the last period of the Middle European Bronze Age, and the Late Urnfield culture is the last period of the Urnfield culture. So it's basically, it's about the 9th century BC. That's basically the last 100 years of Bronze Age before the Iron Age begins. So it's a period of transition and upheaval and maybe social unrest, you never know, in prehistory. The area of the Urnfield culture, which is also the area of my research project, is basically here where you see the black dots from the zone north of the Alps up to middle Germany and from eastern France to the entrance of the Carpathian Basin here. And I've collected rich burials from this area and am analyzing them now. What I basically do is I take all these elite graves and I analyze first the objects found in those graves and the architecture of the graves, the like tumulus or flat grave or whatever. And then I compare their differences and their commonalities. Here I have brought 2 examples just so that we have an image in mind. This is on the left is a grave from France, from Tumulus 9 of Chaveria. On the right is a grave from the eastern region of my area of research, which is grave 3 of Künzing in Lower Bavaria. And as you can see, there are some similarities in the graves, like both of them have swords. This is part of a sword, and here is a complete sword. They both contain pottery. But of course, they also have many differences, like the main one probably being that the one from France is a tumulus grave and the other one is a flat grave. Okay. Building on these analyses and comparisons of the graves, I want to conduct a network analysis. The basis of this analysis is that I see status and identity as relational concepts because status is ascribed and identity is generated in interactions with others. The main network that I'm analyzing is a 2-mode network that consists of graves and object types contained in those graves. On the right, I brought an image. So the lilac ones are the object types, I think, and the mint ones are the graves. So this is just a preliminary visualization. It's an unweighted network and it's undirected. And as I said, a bimodal network, but I also want to analyze other networks, chief among them one-mode projections of this network. But of course also, or probably also other relations, for example, the cultural affiliations that show up in graves or in object types, or the relations between the material of objects and which objects are contained in a grave and stuff like that. Okay, after this short introduction into my PhD project, I hope it's already become clear that archaeological network analysis faces a lot of challenges. One of them comes from the fact that the data is often very complex because the data is not collected for a study that is designed as a network study, as is often the case in sociology. But the analysis usually built upon already existing data sets that can be very detailed and very wide. Also, this data allows for a wide range of thematical subjects and thus study designs. One example for this is that the design that I use, object types and graves, is also used by at least 2 other researchers, archaeologists that I know about, but for completely different purposes, or relatively different purposes. This complex data also leads to complex network structures. 2-mode networks are very common in archaeology. Multimode networks would be something that is like, would be nice if there was more research done into measures, especially for multimode networks. We have multiple types of relationships, and as I've just shown, it would also be desirable in a lot of cases to analyze multiple networks in one study. For this reason, it's essential that we as archaeological network analysts have a way to store and query our data that allows us to concentrate on this diversity that is evident in our data and to fully exploit this potential. And for this reason, I'm using a graph database that is modeled after the CIDOC conceptual reference model. Graph databases are relatively new technology, or, well, maybe not in IT terms, but in digital humanities or archaeologist terms probably. A graph database is a database that uses a graph structure to store data and stores this data in nodes, edges, and attributes. On the right, I've brought for you the property graph model as it's used by a graph database named Neo4j that I use myself. So if you look at the model, this is a exemplary model of books and who has read them and who has written them. And we see we have nodes that are connected by edges. Nodes and edges can have labels. So for example, this node has the labels person and author, while the edge has the label road. And nodes as well as edges can also have attributes, which is all very useful for network analysis. Another advantage of graph databases, in opposition to, for example, relational databases, is that querying chains of connections can be very costly in relational databases, and graph databases are built for this kind of use and therefore have a high performance in this area. The data model is very flexible, can always be extended, which is also very good for research projects because you never know where it might take you. And especially for network analysis, this kind of storing data as nodes and edges introduces relationship-based thinking and the idea of relations very early in the project. So already when you're preparing your data or collecting your data, you already have to think about how it's connected and how it's in relation to other data. And that can lead to very interesting new insights or new ideas about your data. It is possible to do some basic network analysis in the graph database itself. It depends on how well one can do math, actually, because if you can calculate it yourself, you can query it from the database, and then you can, calculate away. But there are also some procedures for example, Neo4j. One is APOC, that enables the graph database to do basic analysis like calculate centralities and stuff like that. But, and that should be stressed, it's not a native network analysis tool. For example, it doesn't have very sophisticated visualization capacities. Here I brought an image of the backend of Neo4j, so it's a little bit fuzzy. But what you see here is basically the data of the object types and the graphs and how they're connected. You have a visual representation of this kind of data and how it's stored. And you can have this row view. Here I asked for the graphs, and on the right it's the count of the number of neighbors. So it's basically the degree of the nodes. So this is what I meant when I said that you can do basic network analysis in the graph database. Okay, the CIDOC conceptual reference model. As we already heard in the introduction, or we heard a couple of things, so I might say some things for the second time, but it's the international recognized standard for the description of concepts from the field of cultural heritage. And as we've already heard, it's been developed for museum knowledge and for museums. So that is some consequences for how it's built and what concepts it can express. It has been developed into an ISO standard. The last official release is version 5.0.4, which I have also linked here. And there's a range of models that extend the CRM or that are compatible with the CRM. I've given two examples, the CIDOC CRM EH or the CRM Archeo, which describes archaeological excavations, which can be used to describe archaeological excavations. There's also an RDF implementation, so if you model your data after the CRM, you can also connect to the whole of the linked open data cloud. One common bias against the CIDOC CRM is that it's often perceived as very complicated, the documentation is very long, it has a very complex structure. Still, I think that it gives a lot of benefits to model your database after the CRM because it's a very commonly used ontology, standard ontology, and when you publish your data in a well-structured manner, this makes it much easier to talk about the data or to share your data because everyone will know what you're talking about. Whereas when you use an own model that no one else knows, then it can be difficult. Okay, here I brought a screenshot of the current version of the CRM, which shows the properties, the entities that can use these properties, and the entities that make up the range of these properties. In looking at this visualization, of course, you always have to keep the inheritance model of the CRM in mind. And we already heard that the properties basically define relations between entities of the CIDOC CRM. So basically, this is already a graph data model. You have the domain, you have the property, which is basically the edge, and then you have, as the next node, the next entity, which makes up the range. So based on this logic, I developed a data model for my domain. Has a couple of specific attributes. For once, the CIDOC CRM is decidedly event-based. So apparently, I didn't know that either, but contrary to public opinion, there's a lot of interaction, a lot of action in museums. Objects are carried around, measured, knowledge is created, all kinds of things. So in this research context that I'm working in, the knowledge that I'm dealing with is more context-based because someone has written it down and I'm just, documenting it. But there's also a focus on documenting the archaeological research process and the results of this research process. Obviously, the structure of this model in part depends on the research questions that I ask from my source material and the requirements that I have because of my network analysis. So I will show that in a second. And also, I did include some shortcuts. Some entities and properties are attributes and not nodes and edges, but in a way that can always be returned to how it's originally in the CRM. So if I would share this data, it would be no problem to go back to the longer definition. I will just show you the main parts of the data model. In the center of the data model stands the E19 physical object, which I use to describe closed contexts. In my case, it's a grave, but in other contexts, it could be a hoard or some other type of deposition. This physical object, E19 physical object, has a type of deposition. Again, in my case, it's always graves. It belongs to a site, which has a site type. And then this site is located at a place, so here's some kind of geographical hierarchy. And then the grave consists of several components. One of them, and this is now in my case, but obviously if I would include other use cases, it could be extended depending on the types of objects contained in other closed contexts. So for me, it's for once biological objects, E20, mostly animal bones, E21 persons, so this would be either cremations or skeletal remains. We have man-made features, E25, so this would be ditches or tumuli or something like that. And of course we have E22, man-made objects, which would be the finds in the grave. There's also some little part here where which deals with the fact that sometimes you have fragments in the grave and which might belong to another object, which might not. And this is a very nice thing about graph databases because the edges can have attributes. I can model this certainty in the edge itself, the certainty that something is a part of something else. Yeah, and then the objects consist of some kind of material, E57. Okay, which part now? This here is one of the parts that I spoke about before, that because of the network analysis that I want to do with my data and because of the requirements I have for my database, I have included some types which would not be normally in the model, but which I need. And this is that because I deal with object types and I assign object types to the different objects found in the graves, I have an additional node which is labeled E55 type, and it's an object. And the objects, E22 man-made objects, can be these kind of object types, but also man-made features, because I also want to include grave architecture in my analysis. And to make it a little bit easier for me to query the database for my network analysis, I have included the relation E19 object, which is found here. So it all goes a little bit faster, and I don't have to type this kind of detour every time. There's also a part that deals with typology and dating of objects and graves, which is here, but which I won't go into too much detail now. And there's a part which is relatively new, which I just added, and I'm not quite so sure yet if that's the best way to model this. Maybe someone here in the room has another idea, which is cultural affiliation. Very often objects, especially in rich graves, will show some attributes that are associated with regions that are not the Unfield culture, but for example the Carpathian Basin or Italy or something like that. And sometimes it will even be imported goods, so this is obviously something that I want to follow up on. And to do that, I created this type of node, E28 conceptual object, which stands for a culture group. And this culture group has a location, which is the region from which it is thought to originate from. Okay, so to make this a little bit clearer, I also have an example, because in theory this is all very theoretical, so I wanted to give an example of how I would map one specific grave. I've only mapped the grave with one find, because otherwise this diagram would be very confusing. But so we have the grave, which is grave A of Künzing. It dates to the Hallstatt B3 period, and the certainty of this assignment that it's Hallstatt B3, which is the late Urnfield culture, I should have said that, is aggregated, because this kind of date comes from all the objects in the grave that I have analyzed, and I've realized that when I aggregate all these dates from the singular objects, then it follows that the grave dates to the late Urnfield culture. The grave is documented by 2 publications, which I have included here, and this kind of node is, or I consider this kind of connection, that something documents something, to be applicable to every element in the database, because there are a lot of things that you would have to give context of where you got them from, like all the periods that we have here that make up the dating part of the model. Like if you for example say late Urnfield culture, this can mean something, or if you say Hallstatt B3, this can mean something different in Germany or in Hungary, for example. So you would have to define and to document which kind of Hallstatt B3 you mean. And you can do that by this kind of documentation. So the object includes, the grave contains some animal bones, in this instance ribs of a pig. We have a person, which is a male cremation, aged mature. We have a ditch, which has dimensions, and it has a position which is enclosing around the grave. And we have a man-made object, which also has a part, which has the object type fragment. And this object has the type toggle, which is a part of horse gear. So not everyone might know what that is. It's you have like the horse gear on the head of the horse, and so the bit doesn't slip out of the horse's mouth. We have like this toggles here, so maybe that makes it clearer. Okay, so this toggle, this specific E22 man-made object, has a type of the type typology, which is the type Kamische-Wacha. which has a broader term, which is angle toggles. The German term is Winkelknebel. I was not entirely sure what the English is, but I think angle toggles is about right. And this type of toggle has traditionally is associated with the so-called Thraco-Cimmerian culture group, which is thought to originate in the North Pontic steppes. So this would all be modeled in this part. As I said before, SEM analysis is possible in the graph database, and this is especially useful in cases when commonly available network analysis software doesn't include the measure that you want to take or doesn't include the pattern that you want to query for. For example, two-mode networks or many network analysis software can't really deal with two-mode networks. And in some cases, you know, like for example, in the case of two-mode clustering, there are also a lot of different equations that you can use. So it's not that there's one right calculation that you can do. So in these cases, it's very useful that you can already query this path with the graph database, and then you can analyze that for yourself. But in other cases, and for more difficult calculations, and of course also for visualization, you would export lists of edges and nodes and import them into network analysis software. Neo4j has several export formats, chief among them CSV and JSON. But if you install this library, Neo4j shell tools, you can also export GraphML. So you basically have all formats that network analysis software can use, almost. Okay, so as an example, I chose the relatively random relation between object types and object materials. So let's say I want to see if there's some kind of interesting connection between the types of objects that are in graves and the material these objects are made of. So first of all, I would go back to the data model and I would look for these nodes and how they are connected, because even though I made the data model myself, I can't really, remember all of it. So we have here, we have the E55 type object, which describes the object types that I've assigned. Then we have to go to the E22 man-made object, and then we go to the E57 material node. This down here is the path in the data model. I hope everyone can see that. It's basically what I said now. So this would actually already be the Cypher. Cypher is the query language for Neo4j. I should have maybe said that in the beginning. So this is basically the Cypher query that you need. And with that, you can already query the database, which I did here. This is the visualization of the query that I just described, and we can already see that there's a very clear focus here. That's the pink one is the materials, the green ones are the object types, and the yellow ones are the E22 objects, the specific objects. So we see in here that this is bronze, this is pottery. It's because I haven't distinguished between different types of pottery, it's all just a big ball of yellow. And then we have some objects made of other materials here and here. So this would be the three-mode visualization of the data. And because most network analysis software can deal with one-mode or two-mode data, we would have to reduce that. But Neo4j gives us here the possibility to contextualize this reduced data in its original context, which I think is very useful. Okay, but the query that we would really use is this one. I don't know if anyone, can you read that? So this is the path. It's a little bit different than the one that I detailed right now because it's too much to type, so I shortened some of the labels in my real database. And then we would return the ID of the object types and the ID of the materials, and we would get a list of around 840 edges. And this we could export as a CSV, and then we would export the node attribute lists, and then we could import that in a data network visualization program. I usually use Visone, and then we would have this network, which, if we go back and look at the visualization in Neo4j, basically it's, you can see the connection. Okay, and then we would have to go on and interpret this visualization, and we could measure and do our analysis and measure centrality and clustering and whatever we want. So to come to the end and to the outlook and conclusion. My next steps for this little project is that I want to adapt and transfer this model to other use cases. There's one specific one I have in mind right now, but there might be others. And in the course of this adaptation process, I think there will be a lot of extending the model as well. And I think there will be a lot of cases that the model maybe can't answer, and then we will deal with that as well. Also, I want to include some other aspects in the model, chief among them the positioning of objects in relation to each other in the graphs, which I think will bring very interesting results. The exploration of more complicated patterns of their position, etc. So in conclusion, I hope I could show you in this little presentation that the challenges of archaeological network analysis require an appropriate way of storing and querying data to grasp the whole complexity of the source material and to get a better understanding of the interactions in this material. So the structured graph databases are very suitable for that because they introduce relationship-based thinking already in the beginning of this kind of research process. And if you have this graph database to store your data for your network analysis, you should model it after a standard ontology, and the CIDOC CRM is the best suited for that. First of all, because it is the standard, but also because it basically already has a graph structure, which makes it very easy to connect these two technologies. To conclude, CIDOC CRM-based graph databases help avoid theoretical and methodological breaks during the conception and analysis of network analysis projects, and they make it easier to understand and to query complex archaeological source material. And with this, I would be finished and waiting for your questions. Thank you very much for your attention.